In a quiet warehouse outside Los Angeles, a machine with hands, arms, and a torso is working beside human employees. It's folding laundry, sorting packages, and learning brand new tasks in real time without being reprogrammed for each one. Nobody expected this breakthrough to come from where it did, not a car company, not a tech giant. It came from a startup almost nobody had even heard of 5 years ago. Its name is Figure, and the robot it built may be the most advanced humanoid machine America has produced. But the real story isn't the metal body or the glowing sensors. It's the invisible system running inside its head. Because building a robot that could walk was never the hardest problem engineers faced. The hardest problem was building one that could actually think for itself. And what happened next surprised even the engineers who spent years building it. This is the story of how a small American company may have solved a 60-year-old problem. To understand why this moment matters, we have to go back to where this dream first began. For most of the 20th century, robots existed, but they lived inside cages, bolted to factory floors. They repeated the same exact motion thousands of times a day, with total precision and zero awareness. They were powerful machines, but they were completely blind to anything outside their strict programming. Engineers dreamed of something very different, a machine shaped like us, working in our spaces. A robot that wouldn't require redesigning the entire world just to be useful inside it. But every serious attempt at this dream ran into the exact same invisible wall. Early humanoid robots from Japan and the United States could walk, wave, even climb stairs confidently. But they couldn't understand what they were actually looking at in front of them. They followed rigid scripts. They didn't adapt when the world didn't match their programming. Ask one to pick up an unfamiliar object, and it would freeze completely, utterly confused. For decades, the gap between moving like a human and thinking like one seemed impossible to close. Then, starting in 2022, a former aerospace and AI entrepreneur named Brett Adcock decided to try anyway. He founded a company called Figure with one bold, almost reckless goal in mind. Build a general-purpose humanoid robot that could genuinely learn, not just blindly execute commands. Investors were skeptical at first. Humanoid robotics had a long, expensive history of public failures. But something had quietly changed in the years right before Figure was even founded. And surprisingly, it had almost nothing to do with robots themselves. It had everything to do with language and how machines were learning to understand it. Around the world, AI researchers had just discovered how to build systems that truly understood instructions. These new systems could describe images, follow complex ideas, and reason in flexible, human-like ways. Figure's engineers asked one bold question that would define everything that followed. What if that same kind of intelligence could be taught to control a physical body? That single idea became the foundation for everything the company would go on to build. So how does a machine like this actually function? Let's break it down simply. At its core, the robot is a bipedal frame, 2 legs, 2 arms, 1 torso. Its head is packed with cameras that constantly scan and interpret the world around it. Dozens of electric actuators act as its muscles, controlling every joint with remarkable precision. That level of fine motor control was once thought to be impossible outside of biology. But the body alone means absolutely nothing without a brain capable of guiding it well. That brain is an AI system trained on massive amounts of real human video footage. Instead of hand-coding every single action, engineers let the robot learn by simply watching. Show it enough examples of a task, and it starts to generalize on its own. It applies what it learned to brand new situations it has genuinely never encountered before. This approach is sometimes called an embodied AI model, and it changes everything about robotics. It links vision, language, and physical action together into one unified decision-making system. In simple terms, the robot doesn't just see a box sitting on a shelf. It understands what that box is, what it's used for, and how to lift it safely. That distinction between recognizing an object and truly understanding it changes everything about robotics. For years, this remained mostly theoretical. Then came the moment that changed everything for good. In 2024 and 2025, Figure unveiled an AI system built specifically for humanoid control. It combined natural language understanding with real-time visual reasoning inside one single system. Engineers could describe a task in plain English and the robot would plan its own steps. No hard-coded instructions. No pre-programmed motion written out for every possible object it might see. Instead, the robot could reason through problems the way a person quietly would. This container is heavier than that one. This surface looks unstable. This job needs 2 hands. That was the breakthrough moment robotics engineers had been chasing for decades without success. It wasn't a faster motor or a stronger mechanical arm that made the difference here. It was a mind capable of adapting on the fly in unpredictable real-world conditions. And the timing of this breakthrough wasn't an accident at all, it was inevitable. It arrived just as large AI language models grew powerful enough to reason about the physical world. Figure had effectively merged 2 separate revolutions, modern AI and humanoid robotics, into one machine. Investors who had once been deeply skeptical suddenly saw something entirely unexpected happening. Figure's valuation soared into the tens of billions of dollars almost overnight. It was backed by some of the biggest and most influential names in artificial intelligence. But raising money is easy compared to proving a robot can actually do real work. That test came next, on the floor of one of the world's most demanding factories. Figure's humanoid robots began working inside a real automotive manufacturing plant, handling actual sheet metal parts. This wasn't a flashy demo on a stage built for cameras and applause. This was genuine production line work where every mistake costs real time and real money. The robots picked up components, positioned them precisely, and adapted when parts weren't placed correctly. Meanwhile, in warehouses across the country, similar humanoid systems began sorting packages for logistics partners. Thousands of units have now been deployed across active pilot programs nationwide. That's a number almost no one predicted this early in the history of humanoid robotics. For engineers who watched robots fail repeatedly outside controlled lab conditions, this felt genuinely stunning. But why does any of this actually matter beyond one single factory floor? Because a robot that can generalize isn't just useful in one warehouse alone. In theory, it could become useful across almost any physical environment imaginable. Logistics companies are exploring humanoids for repetitive lifting tasks that are hard to staff. These are jobs that are physically taxing and difficult to fill with human workers consistently. Manufacturers are exploring them for tasks that are dangerous, awkward, or extremely precision-heavy. Some researchers believe home assistance robots could eventually follow this same technological path. Robots that could help with chores, mobility support, or care for aging individuals at home. None of this is guaranteed yet, but the technical foundation now actually exists. For the first time, what once sounded like science fiction has been physically demonstrated. Economists studying automation say humanoid robots could reshape entire unpredictable industries over time. Food service, retail, elder care, even light construction could all eventually be affected. The appeal here is simple and surprisingly elegant when you really think about it. Instead of redesigning a warehouse around a robot's limitations, you build a robot that adapts. That is a fundamentally different philosophy than the rigid industrial robots of the past. But before we get too excited, we need to talk about what still isn't solved. Because the challenges facing this technology right now are genuinely, seriously real. The first major problem is cost. These machines are extremely expensive to build today. Dozens of precision actuators, advanced sensors, and onboard AI computing all add up fast. Some current builds are estimated to cost tens of thousands of dollars per single unit. Mass production that could drive that price down is still likely years away from now. The second problem is reliability in situations these systems have simply never encountered before. AI systems that generalize well in DMOS can still struggle with rare, unpredictable situations. A robot that's never seen a spilled liquid or a broken object may still make mistakes. Safety is a serious concern too, especially for machines working closely near real people. A 200-pound humanoid robot must never cause harm, even in edge cases it wasn't trained for. Engineers are still developing rigorous safety systems to guarantee that outcome consistently every single time. Then there's the manufacturing challenge itself, which is arguably the hardest problem of all. Building thousands of complex robots at consistent quality is something no company has fully solved. Even simpler electric vehicles took years to reach stable, high-volume manufacturing production. A robot built from thousands of precision components is a far, far harder challenge. Supply chains for specialized parts, like precision joints, are still maturing at a slow pace. Long lead times for critical components continue to genuinely slow expansion efforts across the industry. And perhaps the biggest unanswered question of all remains frustratingly unresolved for now. Can these robots operate reliably, day after day, without constant, close human supervision nearby? Right now, most deployments still involve close human oversight at almost every single stage. Full independence remains a genuine future goal, not yet a current, working reality. These aren't small obstacles to overcome. They're the same walls that ended earlier robotics dreams? But this time, something feels genuinely different about the trajectory of this technology. The AI brain behind the robot keeps quietly improving itself with every single deployment. That one simple fact may be what finally lets humanoid robotics succeed where past attempts failed. So what happens next? Where does this rapidly evolving technology actually go from here? Engineers are already working on faster, more efficient AI models for future generations. These models could let robots complete tasks with far less human guidance required overall. Future versions may be lighter, more power efficient, and capable of running for much longer. Researchers are exploring how robots could learn brand new skills simply by watching video footage. If that becomes reliable, it could dramatically shorten the time needed to train new skills. Some companies are targeting the end of this decade for meaningfully lower production costs. Lower costs could eventually open the door to genuinely wider, more mainstream adoption. Analysts caution that consumer availability for home use still remains realistically years away. Most credible timelines point toward the very end of this decade at the earliest. Others across the industry are racing toward this exact same ambitious goal right now. Major automakers and leading AI labs are creating fierce competition across the entire field. That competition matters deeply because no single company controls how fast this technology moves. Whether Figure remains the clear leader or a competitor eventually overtakes it, one thing stays true. The underlying breakthrough, machines that can reason about the physical world, isn't going anywhere. We are witnessing the earliest chapter of a technology that could reshape physical work. This shift could quietly transform how everyday jobs get done across America over time. And that brings us to the much bigger question sitting underneath all of this progress. For most of human history, machines have done exactly what we told them to do. Nothing more, nothing less, and never anything they weren't explicitly programmed to handle. For the first time, a machine built in an American lab can look at something new. It can reason through an unfamiliar task and figure out what to do on its own. That is not just an engineering milestone worth celebrating. It's a genuine shift in what a machine is. The question is no longer simply, can we build a robot that looks human? It's now, what happens when robots begin to think like us, even just a little? Nobody expected America to build this. Not this fast and not this capable. And certainly not from a company most people had never even heard of before. But here it is, walking, learning, and quietly changing what the future of work looks like. Inside factories, inside warehouses, and possibly, one day, inside our own homes. The engineers behind this technology are careful not to overpromise what comes next. They know real breakthroughs take years of testing, failure, and quiet, patient refinement. But for the first time in decades, the destination finally feels within reach. The next chapter of this story hasn't been written yet by anyone. And that uncertainty might be the single most fascinating part of this entire story.